Thanks everybody for having me. My name is Dr. Brach Poston. I'm an assistant professor at UNLV, and the title of my talk is Transcranial Direct Current Stimulation as a Treatment for Parkinson's Disease. So this is an outline of what I'm going to talk about in my talk. I'm going to give just a very brief overview of what the technique is and a little bit of history of it. I'm going to talk about the methodology of applying it and some of the advantages of this method as an adjunct treatment for Parkinson's disease. Talk a little bit about the effectiveness of it compared to some other measures. And then I'm going to talk about some of the research that I and other people around the world have done on this technique, which will lead to a clinical trial that we currently have going on right now, funded by NIH, that we're doing at UNLV. That maybe some people would qualify for or be interested in. Okay, so just as an overview, this is a non-invasive, painless technique. So this is not deep brain stimulation. This is a non-invasive, painless technique where a couple of electrodes are put on someone's head like this, basically sponges with rubber inserts that are dipped in salt water. So very easy to apply, and connected to basically a battery-driven computerized device that runs it. So it's pretty easy to put on, something that a patient or caregiver could even do to themselves eventually. So this is a non-invasive, fairly easy to apply technique with just basic training. Original studies were done in younger adults, but a lot of studies have been done in a lot of populations on stroke and others. And the general idea is that if you apply this stimulation either before or during practicing a motor task, it usually leads to about a 10 or 15% increase in motor skill than what just practicing the task alone could give. So the idea is that for different populations, if you apply this while you're doing rehabilitation or while you're practicing motor tasks, that it can enhance those activities above and beyond what they would do on their own. So one important thing we'll talk about a few times is that on a one-time basis, like after applying it for about 20 minutes, you get about a 10 or 15% improvement in, say, hand function. So activities of daily living with the hands. Some studies in other populations where if you apply it day after day for, say, 5 days or a week or something like that, you get a much bigger improvement. So we'll see later that's going to be an important thing that we're looking at is what would happen when we apply it for a few weeks. Do we get a clinical, meaningful improvement that someone can see in daily life that would be big enough to notice and make it worthwhile? All right, so this is a new variation of older electrical stimulation techniques. The general idea is to apply this for about 20 minutes at a time. So just putting it on the head for about 20 minutes over a certain area of interest. Usually the primary motor cortex, because that is basically the brain structure at the top of the hierarchy for controlling skilled movement with the hands. And the general idea usually is that increasing the excitability of the neurons of primary motor cortex by putting that red electrode over primary motor cortex to excite the neurons beneath it. And that, at least in the short term, increases performance usually. So normally when people practice a motor task, say with their hands, the neurons that control those muscles in primary motor cortex get more excitable with use. So this is a way of applying an external current at the same time that's going on to further boost that normal excitability of those neurons that control those muscles. They get more excitable with practice to further increase performance. So that's one of the underlying physiological mechanisms of why it may increase motor performance. So that's the general idea behind it. So why would we want to study this in motor disorders? Well, some of the reasons is that current treatments for a lot of disorders, including Parkinson's disease, are somewhat effective, or they have side effects, or they're very expensive and they're not easy to use, or you need trained technicians to do them, or you need really expensive equipment. This is a pretty simple, easy to use device that is affordable for almost anyone. The other thing is, if you really think about it, if you think about other than pharmacological agents or surgery, other than exercise, there's really no other ways, interventions to improve performance in some of these disorders, including Parkinson's. So this is one of the few other things that is not a drug and not a surgery that has a lot of studies that have been done on it that show increases in performance. So when I first started studying this about 7 or 8 years ago, there were maybe 10 or 15 studies on the topic in total. Now there's probably over 1,000 studies done around the world per year, maybe more. It's just been exponentially increasing the number of studies in all kinds of different populations for all kinds of different purposes with this technique and things like it. So it's a pretty popular area of research with a lot of promise right now. The other thing is that it's been shown to be effective. But just a little brief history, just for a little bit of background. So actually, you know, you may think that stimulating the brain with electric fields is new, something that we do in the age of technology, but actually way back in Roman and ancient Greek times, they played around with putting live torpedo fish on people's heads to treat headache or depression. And the method was forgotten about for hundreds of years, and then it would get revived somewhere, used again, for instance, in the 1700s, 1800s, forgot about, revived again. This was a device around the turn of the century that you see is a little unuseful for everyday uses and pretty crude, but it was used around 1900 at Johns Hopkins to stimulate the brain. A few years ago, with the advent of fMRI and with another brain stimulation technique we do that I won't talk too much about today, transcranial magnetic stimulation, where you can actually measure different pathways in the brain, you can actually take safety measures and things like that. That sort of made a revival of transcranial direct current stimulation, because as opposed to during the 50s or 60s, when those other methods weren't there, now when we apply the direct current stimulation, we can measure other things. People can do the safety studies that they've already done and things like that. So it's kind of renewed interest in it. And like I said, the amount of research in this area has really exploded lately because of this. So, you know, they can see like what areas are actually activated when you do the stimulation, how does the excitability of neurons change in that top one when you do the stimulation and things like that. All right, so just very briefly, general mechanisms of how this may work in Parkinson's disease. We already mentioned that the short-term effects may be due to increasing the excitability of the brain region that we stimulate. In this case, we stimulate the motor cortex, which is the primary governor of skilled movement execution. However, when done day after day, it's thought that it may induce changes in various proteins and various receptor systems and various connections between cells that also may underlie improvements in performance. Some of the others is induce remote changes in anatomically connected brain regions. So if you see, for instance, in some of these, where you put it on motor cortex up there, motor cortex is right beneath the surface, but areas like basal ganglia are very deep, and the current doesn't reach them. However, motor cortex is connected to basal ganglia and other areas like cerebellum. So when you stimulate that area, those other areas do get stimulation indirectly. And some studies in rats and monkeys have shown changes in basal ganglia, for instance, when you give stimulation to the motor cortex, even though it's not directly stimulated. One study in monkeys, for instance, even showed increased dopamine production with 10 days of stimulation, I believe. So it can induce effects in other regions. So that may be one reason why it may work, but those studies are pretty difficult to do in humans as far as actually what is happening. We can look at the performance a lot easier. So that's one mechanism. Another mechanism is in Parkinson's patients. If you take a big group of patients and you have them do motor tasks and you measure their activity in, say, primary motor cortex and cerebellum, you see patients who perform better generally have higher activity in motor cortex and cerebellum. And it's thought that that is a natural compensatory mechanism that the body does to make up for reduced basal ganglia output. So it's sort of like if you had a basketball team and one person got injured, the other people have to play harder to keep up the same performance for the team. Those areas are more overactive in some patients, and those are the same patients that usually do better on motor tasks, that have that enhanced activity in those other areas as to compensate, as opposed to some patients who, for whatever reason, those areas don't increase their activation to help do motor tasks. So therefore, it's thought that maybe when we stimulate these areas that we're helping with that natural compensation by exciting them and getting them to work more. So that's, at least theoretically, some of the reasons why we may see performance benefits with this stimulation. Another issue with the stimulation is that this wouldn't be too effective. It could still be used, but it wouldn't have nearly the amount of practical use if it only worked while you were getting stimulation, right? Because you may not always be able to give stimulation when you're doing some activity or going somewhere or whatever it may be. But some of the original studies this shows here just brain excitability getting measured with another technique after stimulation ends, showing how long after stimulation ends. If we just look at the longest stimulation period they used, which is these filled squares, they applied stimulation for 13 minutes in this case. The stimulation ended here at time 0. And then they measured the increase in excitability after the stimulation ended. And you see that it stayed enhanced for at least 90 minutes afterwards. So since that excitability is usually correlated with increases in performance, this basically showed that if you give it just one time for about 20 minutes, you should get an increase in excitability and performance for about 90 minutes afterwards. Now we're going to talk what happens when you do that day after day. But just a one-time application usually increases excitability about 50% and performance about 10% for about an hour and a half afterwards or during practice. All right, so if you see here, there's different devices. We showed a few, but in general, they're pretty small devices. They're about this big or so. So they're a small battery-operated device, so very easy to carry around and use. And you place electrodes on, in this case, motor cortex, and then one over the eyebrow to pass a current between them to excite the area underneath. And then you just basically have a headband and a chin strap or some sort of cap to keep them in place for the 20 minutes. So in general, that's how it works. So there shows a typical setup. You have the device, and it's just connected to 2 electrodes on the head. Now, why is this important? So it's very portable, also safe, easy to apply, and can be given during a task. So I'm not really going to talk about it, but there's other brain stimulation methods like repetitive transcranial magnetic stimulation that's approved for treatment of depression, for instance. It's also used in Parkinson's disease. However, that device involves a big chair that you're sitting in and a big magnetic stimulator that's about half as big as my body sitting beside the chair, and a trained operator, and it costs $100,000. And it doesn't even work as well. So they did a lot of studies on it, and they found that it worked a little bit, but not really that well. But this is the practicality of it. Yes, you could have something like that at a clinic or 2 in town or something like that, but it's not going to be something that can be used by a lot of patients, everywhere. However, this method, since it's so little and small, could potentially be used by patients in the home. Research-grade devices could be bought even for $400, and the minimal sort of device all the way down to $10. So basically, these things could be manufactured for between $10 and $400 that would be good enough for personal use. Maybe not for research or high-level research, depending on what measurements you're making, but they are affordable where, unlike a lot of things that are studied in science, that if this would be shown to work well enough, it could be used in the real world, unlike, for instance, that other method I just mentioned. So that's some advantages of it. So when I was at the National Institutes of Health, we were looking at the other method, repetitive transcranial magnetic stimulation with the big chair and device. And there was 3 studies done by other people, not me at the time. 2 transcranial magnetic stimulation studies and 1 TDCS study, and the TDCS study basically worked the best. So in addition to those other advantages, it was also the most effective of those techniques. All right, so we sort of gave an overview of what the technique is, how it works when you give it maybe for one time for 20 minutes. It may improve your hand function by around 10% or so. But what happens if you give it chronically? Would it work better is kind of what we're going to get into now. So this is the original classic study, also done at NIH by a different research group, not by me. It was done about a year before I got there. And this had two groups of young adults practice a difficult task, kind of like a video game on a computer with their hands. And we have the group that got fake stimulation, sham stimulation. They thought they were getting real stimulation. It felt the same, but it was not really on. Versus a group who got the real stimulation. And you see that after 5 days, the effects sort of became cumulative day to day, giving 20 minutes of stimulation a day. And you see by the 5th day, the group that got stimulation got to about 20, 30, 40% higher level of motor performance than the group who got the sham stimulation. You also see the other group reached a plateau. Both groups sort of plateaued, but the group that got stimulation plateaued at a higher than normal natural level. Basically what was concluded is that the stimulation could increase motor skill performance in healthy subjects to a greater degree than just practicing a motor task. So sort of an external way of increasing the total amount of learning someone could have in a motor task. So this would be important, obviously, for rehab. You could get better at doing rehab or doing skills of daily activity if this would work in patients. So this was done in healthy young people, which you may say, okay, it may not be really relevant. It could be right. However, other studies they did usually showed that the more impaired a person or the more impaired a patient or the older a person, if they compared 65-year-olds versus 80-year-olds, the more impaired or older someone was, the more likely it was to work. Probably because those sort of people had more room for improvement because they were operating at a lower level. So the fact that it could increase performance in young people who should be performing at a high level already, don't have any impairments, it actually most likely is more likely that it could increase performance like that to a greater degree in an impaired population. So that's the hope. So that was one study done. Also, after this, they measured how long did people retain that increase in performance in those groups. So this shows the stimulation group with the top trace, and you see that they kept the advantage in performance for up to 85 days afterwards. However, their decline in performance, because now they weren't practicing the task anymore, so they're getting a little worse at the task because they're not practicing it day to day. They did get worse, as did the other groups. So the rate of decay in motor skill was the same, the rate. However, the group that got stimulation was still always better because they're coming down from a higher level. So they got to a higher level, and since they were declining at the same rate of the other group, they always had more skill even up to 85 days afterwards. So therefore, the hope would be that maybe you could do the stimulation for a week or two, take a couple weeks off, you'd still maintain most of what you gained. Do it another 2 weeks, take 2 weeks off where you wouldn't have to do it every day, for instance, although maybe it would work better doing it every day. But this at least gave a little bit of hope and promise that if you do daily stimulation, you get cumulative effects where the difference in performance with stimulation is now maybe 20 to 40% better instead of just 10% better if it were just done for one day. So that's some of the theoretical underpinnings of what people are trying to do, including myself, with this stimulation and research studies now. All right, this is just another study. This is a follow-up study. It showed the same thing. The group that got stimulation got to about a 30% higher level than the group who did not get brain stimulation. This was also in young people. All right, so around the same time, some different research groups thought to apply this in Parkinson's disease to build on results from young adults. This just shows a one-time application. This was done at Harvard. They measured the UPDRS, a reaction time task, and a Purdue pegboard test. And you can see that in general, the group that got the stimulation got about a 10 or 15% improvement in performance on a one-time basis, one 20-minute application, improved their UPDRS score, and they controlled their hands in a pegboard test and in a reaction time test, about 10 or 15%. So a few years later, I started working in this area. There was only 4 or 5 studies on this and Parkinson's disease at the time, and they sort of used a lot of different methodologies. So I wanted to sort of start from the beginning and use a basic methodology, but also trying to just determine what some of the basic parameters would be that would give the best results. Because other studies had used all kinds of different parameters. Some use the high current, some use the low current, some use 10 minutes, some use 20 minutes, things like that. Some applied the stimulation before someone practiced, some applied it at the same time someone practiced the task. So my basic idea is we at least got to determine what works best on a one-time basis, because most likely that would be what you'd want to use for a long-term study on a long-term basis. Yeah, maybe they wouldn't be the same, but that you wouldn't want to use what didn't work as well on a one-time basis than try it long-term, doing it the other way. So the main things I was trying to find out with these initial studies that were funded by Michael J. Fox Foundation was, what's the best time to do it? Do you want to do the stimulation before you practice the task or while you're practicing? And then also, do you want to use a 1 milliamp current or a 2 milliamp current? Both are really low currents, but this was sort of the range being used at the time to see which one was better. So when I originally did these studies, I thought that doing it during would be better, and I thought that a 2 milliamp current would be better. However, the results basically showed there wasn't any difference. They both worked equally well. So here in this plot, I have sham stimulation. So these were the same people. They came 3 times a week apart, counterbalanced order. They each got a fake stimulation one day, and then they practiced before and after another day. And you see as a percentage of the day that they didn't get stimulation, you see once again about a 10 or 15% improvement in performance. And it really didn't matter whether they did it before they practiced or during practice. And it really didn't matter whether it was 1 milliamp or 2 milliamps. These weren't different from each other. There's only a 1 or 2% difference or something like that between them. So it wasn't what I originally thought would happen, but actually it's probably better, because if it worked before you practice something and at the same time, that gives you a lot more flexibility in real life if you were doing something. Probably all think of situations where maybe you wouldn't want to do stimulation while you were practicing something. An easy example is a sporting event. If we were talking about athletes or something, you wouldn't be able to wear the device out during your event, but if you could do it beforehand and get the same thing, then you could do it beforehand and you go out for your event. But so there's various situations. So it wasn't exactly what I thought would happen, but actually probably better that those parameters both work. They don't really matter exactly. So once I got those few out of the way, my next step was to determine what else is missing in the literature, and then use those parameters and then try to fill in those other gaps in a long-term study. All right, so if I just look at what everyone else was doing and what was missing in the literature, a few other things came up about what happens to the opposite hand when you're stimulating this hemisphere. It's mainly working on increasing motor skill in the contralateral hand, because these connections from motor cortex cross over your brainstem and affect the other hand. There's not a whole lot of connections on the same side, but usually only one side is stimulated. However, that side of the brain is more dominant for motor planning, so it may not matter. So I was going to look at the other hand. And also, most of the studies have been done off medications that were successful. They hadn't really studied on medications. So another thing I want to do is see, will the stimulation work just as well when the patient is on medications, because that is how they would be doing it in real life. They're not going to go off medications. So those were some of the other gaps that I decided to try to fill in my current project I'm going to talk about, along with using these parameters that I found to be the most effective and most practical. All right, so the basic idea, just as a reminder, is that we're trying to determine what is the best method to use to get a short-term improvement on a one-time basis, and then use those parameters of stimulation on a long-term basis in Parkinson's disease to see if we can get those 10 or 15% improvements in performance to build on each other like in the young study, cumulative effects day to day to get up to a clinically significant level of 20 to 40%. Is the general idea of trying to do. And then maybe someone could do the stimulation for a week or two at a time, not have to do it another week or two, and then do it again. All right, so I designed a study that I'm going to talk about next, but right when I was getting ready to start my study, a group in Italy actually came out with a really good study that was similar to design to what I looked at, so just figured I would mention it real quick. This was a study where patients got stimulation for 5 days, and they were looking at freezing of gait. So they're trying to see, would giving the stimulation reduce freezing of gait if the stimulation was given for 5 days in a row. So this is a well-designed study, double-blind crossover. And you see that the group that got stimulation, the anodal TDCS group here, they had basically a lot less incidences of freezing of gait. At the end of the training, 5 days especially, 7 days, and then 2 and 4 weeks after. So they got stimulation for 5 days. It reduced freezing of gait a pretty good amount, looks like about 40% or so. And then that was able to be maintained for about a month after the stimulation ended. So that's a very promising and good study. The one downside to the study is they only looked at freezing of gait. There could be a lot of possible parameters you would look at. They only looked at freezing of gait, but nonetheless, a very promising result in a long-term study. All right, so that brings me to my current study that we're trying to look at this issue, and this is something we have going on right now. There's a few people in the room who have done the study or similar ones to this. So this is one of the reasons for the talk is if anyone would want to do this study, please contact me. So we're looking at long-term application of this technique to see if we can get the cumulative effects. It's basically 2 weeks of stimulation. I'm the principal investigator. Dr. Zoltan Mari is a co-investigator, and Dr. Landers is a co-investigator. All right, so just as an overview, this is a government grant from the National Institutes of Health, the National Institute of Neurological Disorders and Stroke, and it's also a clinical trial now. So this is funded by these government institutes, and it is a clinical trial. I believe it's a stage 2 clinical trial. All right, I already mentioned those. So this is the design of the study. Just as far as inclusion-exclusion criteria, we can take people that are 55 to 80 years old, can't have a deep brain stimulator because obviously the electric and magnetic fields that would be given during the study would disrupt that, and can't have a pacemaker or metal in the head like if you had shrapnel or something like that. Dental fillings are fine having those, so we can't use people for those, no seizure history. So basically how this works is the people will come in on the first day and they have a testing day. That would be the baseline there. And this is sort of a longer session because it's testing. And then they get 2 weeks of stimulation and practice. So you practice 2 motor tasks while you're getting stimulation. So we're trying to see, does the stimulation improve those motor tasks to a level greater than practice alone? We're using a pinch grip task like used in some of the other studies. We're also using a handwriting task. So as everyone probably knows, handwriting is one of the major motor tasks that are impaired in Parkinson's disease, and it's pretty well studied because of that. So we're looking at a handwriting task that was developed by a top researcher in Belgium that we're working with. And you practice those tasks for basically 9 practice days with the weekend off for 20 minutes at a time while getting stimulation. So we're trying to see, will the group that gets the stimulation get to a higher skill level? At the end of that 2-week period, we have another testing day where we test, and then there's a 2-week break and we have post-test to see will any effects of the stimulation, will that be able to be maintained for 2 or 4 weeks after stimulation ends. So see, is there retention of it? And if there is, then maybe you would need to do the stimulation all the time. You could just do a duty cycle of, say, 2 weeks on, 2 weeks off, or something like that. So that's the design of the study. So if someone was doing this study, it's basically a 2-week study with a couple of follow-ups. These practice days only take about 30 minutes, where the testing days, the 4 in red, take about 3 hours or so. But the other days in gray there are very short, only about 30 minutes. We don't need to go through this, but basically on the testing days, we test people on and off medication. That's those reds there. We're basically testing not only on the tasks that people practice, but also on tasks they didn't practice. So it would be good if the stimulation improves tasks that you did while you're getting stimulated and you practiced, but it would be better if it could improve motor tasks that you didn't practice and didn't do during stimulation also. If there was a generalization effect or a global effect, that would make it a lot more valuable stimulation, because you wouldn't be able to get stimulation during every task of daily living that's impaired, right? You want some sort of carryover to tasks that weren't done during stimulation. So those are sort of the things that we look at on those test days and why they're longer. And we also take measures of motor cortex using TMS to see what pathways in the brain may have changed with the stimulation. There's a lot of pathways in motor cortex that we can measure non-invasively with TMS that are impaired in Parkinson's disease, so they're different than in normals. And we think that maybe the stimulation may make some of those pathways, some of the responses we get when we do the tests, more like normal adults. So then we can correlate the changes in those specific pathways to the changes in performance, is the general idea. But that's the general design of the study. It's a test day. Don't really need to go through this, but a practice day is only about 30 minutes. Just come in, get stimulation, and practice some motor tasks. So handwriting and pinch grip tasks during stimulation. Those days are all on medications. All right, so that is basically an overview of the major study we're doing right now with this technique, and an overview of the technique. Be glad to take any questions anyone may have on it. This would be an adjunct treatment for the disease, obviously. It's not going to be something by itself. So it's something to help with other things, medications, exercise, rehabilitation, things like that. It will hopefully make those work better to a significant degree. Yeah, people can buy them. I don't know if I recommend it or don't recommend it, but no, they can be bought. So I think the one that's research grade, that is used in research, costs about $400, but they're made for down to $10. So people can buy them. Some people could probably figure out how to use them without any coaching at all from someone who's done it. Some may not, so I'm a little hesitant to say someone should do that. You know, the reason for doing this research is to see, does it really work, and doing that in a controlled manner versus just someone trying it, maybe being a placebo effect or not doing it quite right. So that's the whole reason for doing the research, is that hopefully, eventually, if we know that it works, then we could recommend people to buy it or tell people how to do it.
Okay, so the doctors don't recommend it right now?
No, a doctor definitely is not going to just say, hey, go do one, because most people are not going to read a bunch of scientific papers and determine the optimal way to do it on their own. It's going to be pretty hard to do, to look up papers on PubMed and do it. But someone could, like sometimes people that do our studies, they, once they've done it a few times, they pretty much know like how to put it on almost. And if we tell them a few little details about how to do it, they could potentially do it on their own. And if they want to, that's up to them. We tell them the way to do it, but.
So basically, okay, I understand what you're saying.
Yeah.
That's the first part. So.
Yeah, so, before we would recommend it, we need more studies like the one we're doing to determine exactly what it does and stuff before we really recommend it. And, people are using it for playing video games. People are wearing them playing video games. Kids wear them for more than's been done in the scientific literature. So it's a little, it's a totally safe, there's never been anything happen. Studies like the current level is like 1,000 times less than would cause neural damage. But, I don't know if a kid uses it 8 hours a day versus 20 minutes a day.
No, but while we're talking about Parkinson's disease, then it's not recommended right now because you don't know exactly what it is, and it might be complicated to use.
Complicated in doing it exactly perfectly first. Not complicated compared to other things. But yeah, for someone to figure out on their own without any input, just by reading studies and looking at some things on the internet.
So it's basically the same thing that Larry did.
Yeah. So Larry did these. Larry did these. Larry did both of those things.
Right. So we used to love them.
Yeah. So.
We loved them.
Yep.
Brach, does this work on all stages of Parkinson's disease?
That's something it's a good question. So that's something that hasn't been looked at in detail. Usually we're looking at the initial few stages just because to have a group that's pretty much the same, but my probably really advanced stages, it's not going to help in really advanced stages. It's too late by then, and the increases, if there were any, would be too small to make a difference by that time. This would probably be something, it's stages 1 to 3 of the disease, but yeah, that's something people have always mentioned that should be looked at, but it's a difficult one to look at, for sure. But it's not that. I've just always done fine motor with the hands in all my academic training. So when I apply for grants, if I say I'm going to do that, he has a lot of knowledge on that. He has a lot of papers on that. If I would try to do others, that they may criticize that guy hasn't done research on walking before. So those are reasons why I'm looking mainly at the hands, but other research groups, we do have some studies we're looking at walking. So the other research groups have looked at things with walking, and one did dancing and stuff like that. So that's a big question, is will it work for gross motor skills like it will for fine motor skills? Right now, I just off the top of my head of maybe the 10 studies that have been done on those, probably 7 or 8 have shown a positive effect. So there is promise that they can. But the studies are designed different. Some of them aren't designed the best. That's why I showed this one from Italy, because it was designed really well, because it was a double-blind, sham-controlled. It was a crossover. I didn't get into the real details of it, but it was a crossover. So they had the same people get fake stimulation for a while, and then they did the real, and other people started with the real, then did the fake, so that you get rid of all the possible inter-individual differences in brain morphology that could play into the results. So that was another really good aspect of this study in Italy with freezing and gait. And they did 5 days of stimulation, so also good, so that's promising, and it's a pretty big effect. So I would say tentatively right now it does seem to work fairly well on gross motor abilities also.
So that's 15 yards or 20 yards. Is that 15 yards further or 20 yards further?
Like is how big the step forward is it? Maybe probably 50. It's promising. It's just that we need more. These are difficult to do, take a long time. Just the time spent to write grants and get funding for them alone, or a year or two before, even if you get it, and it takes several years to do it. I mean, it's slower than we'd like, but that's like the best we can do right now. It's just to do the studies, do the